Hello friends, in this video we are going to discuss about Grad B drift. Okay, so or you can say motion of single particle in non-uniform magnetic field. Okay, so I would like to request you to watch the video of lecture 4 where I have discussed about single particle motion in uniform magnetic field. Okay, before you watch this video I would like to request you to watch that. Okay, and link of that video is given in the description box, so you may visit the link and you should watch that video. Okay, so let's start the topic. Now let us discuss Grad B drift. So here is the x-axis and this is the y-axis, and the magnetic field is being applied along z-axis. This is the z-axis which is coming out of the screen. Okay, out of the page, you can consider it is coming out of the page. And magnetic field lines are, suppose when we circulate these dots represents the magnetic field lines. Okay, it is coming out of the page. If you draw like this, then it is going into the page, and if it is dot, then it is coming out of the page. Okay, you can use those symbols to represent this. Okay, so these are the magnetic field lines. Okay, so gradient, this is gradient of magnetic field, Grad B. Okay, so the magnetic field varies along y-axis. Okay, so here you see. Now in order to discuss this, first we must know some results that we have got in uniform field. Okay, in uniform B field, single particle motion in uniform B field. So we must have the so here I'm not going to derive those expression again, so that's why I would like to request you to watch the lecture 4. So I will write the results directly here. Okay, then I will proceed. Okay, so when the magnetic field, this B field was uniform, when B field is uniform, then what are the results we have got? We have got here V of x, V perpendicular, e to the power I omega ct, and also we got Vy plus minus I V perpendicular e to the power I omega ct. So these two results we have got, and also we got x minus x naught is equal to e to the power here V perpendicular by wc e to the power I omega ct, and also we have got y minus y naught is equal to plus minus V perpendicular omega c e to the power I omega ct. So those results we have got in when the magnetic field was uniform. In lecture 4 we have already discussed. So in exam you have to start from there. Okay, you have to show how to obtain those expressions. Okay, so that's why watch that video. Then from that, so now we will proceed from here. So now you see, so what to do in this case. Now look at this. In this case, magnetic field lines of force are straight, but density increases in y direction. Those magnetic field lines, density of those magnetic field lines increases in y direction, and magnetic field gradient is what does magnetic field gradient mean? Okay, what does it mean, this magnetic field gradient? It represents the variation of magnetic field line density. Okay, so hope you have understood that point. Okay, in this case what will happen, the due to the gradient in magnetic field, okay, the Larmor radius to be greater at the bottom of the orbit, and at the top it will be smaller. Okay, and for ion, so now you see, in this case, suppose this is a particle, it is moving, ion, suppose is moving in this region like this. Okay, so here, so if a particle moves in this region, it travels in this region. Okay, here the Larmor radius will be smaller, larger, not here is smaller, here it will be larger. If suppose this is the ion, and where in the region in which the density is less, the density of the magnetic field lines is less in that region. Okay, the Larmor radius will be smaller. Okay, greater. Larmor radius will be greater like this. Okay, and the region where this density is maximum, density is greater, density of the magnetic lines of force, there the Larmor radius will be comparatively smaller. Okay, so, and this drift of guiding center will occur in the direction perpendicular to the, now you see, this is the direction of grade B, and the direction of the magnetic field is in this direction, and in x direction, in which is perpendicular to both the magnetic field and the variation of magnetic field, in that direction the drifting takes place. Okay, drifting of guiding center takes place. It is different for different surges, and if it is for ion, it is in this direction, and for electron it will be in this direction. Okay, so hope you have understood this. So now let us discuss the mathematical part. Okay, now you see, you know, this F force is equal to Q. If the charge is Q, then moving with velocity v, then it is given by Q into V cross B. Okay, V cross B. Now you see, so this can be resolved into three components: f of x, x cap, plus f of y, fy, y cap, plus fz, z cap, is equal to Q into, so V cross B. So V cross B, it can be obtained here, x cap, y cap, z cap, and here Vx, Vy, Vz, and here we have 0, 0, Bz, sorry, because magnetic field is being applied in z direction only, so that's why Bz, and in other two directions it will be 0. And if you calculate this, then you must get this expression. So let me scroll up a little bit. Okay, so Q Vy Bz minus Q Vx Bz, and then you will get 0. Okay, so our result will be, so that means if you multiply Q, okay, here if you multiply Q, you will get this. Okay, not only this part, if you multiply here Q, then you will get this. Okay, so we got here Vy Bz minus Q Vx Bz. Now here we are discussing about grade B drift, isn't it? Grade B drift. As the grade B is along y direction, So that's why we will take the y component only. Okay, we will take this fy only. Okay, so here we need fy is equal to minus q v x b z. So this is the y component. Okay, so hope you have understood this. So now you see, so let me clean this part here. Okay, also this part. Okay, now you see, we know that e to the power I omega ct, that's equal to cos omega ct plus I sin omega ct. Okay, so if you put this value here, and here, okay, and if you take the real part only, okay, if you take the real part only, then this vx can be replaced by can be replaced by this one. Okay, so let me write here minus q v perpendicular cos omega ct into bz. Okay, so we will get this. Okay, so taking the real parts only. So what we have taken here, we have taken the real parts only. So this one will be v perpendicular cos omega ct. Okay, so hope you have understood this. So now here you see this one will be equal to Larmor radius r sin omega ct, and this one will be equal to minus plus rl cos omega ct. Okay, cos omega ct. So we don't need this. Okay, so or you can, if you want to write, then you can write this. Okay, also so here it will be if you take this one here, it will be minus plus I v perpendicular sin omega ct. Okay, because here you see there is I here, I, so if you multiply here I, it will be minus 1, and one I will be here. So that's why in this case this one will be imaginary part, not the sign. Okay, so hope you have understood this. So now here you see this magnetic field density, lines density, varies along y-axis. Okay, so suppose according to Taylor, we know the Taylor series. Okay, when a function varies in a particular direction, then what happens? So f of y, it is given by f of y naught plus y minus y naught del f del y, and plus y minus y naught factorial 2 square here, y minus y naught whole square, then second partial derivative of del f del 2f by, here we will get del y, actually it should be y. Okay, so here you see, and it goes on. Okay, so if you apply this in case of magnetic field, so here we are taking the z component only because the magnetic field is along z direction, isn't it? So then we can write b plus y minus y naught del b by del y. Okay, del b by del y, and the remaining parts will be neglected. Okay, so here we have used Taylor series. Okay, now let us use this bz here, then we will get f of y is equal to minus q v perpendicular cos omega c t, then b plus y minus y naught into del b by del y. So here del b by del y, let us use this curl bracket here. So now you see, so here you see from this equation y minus y naught, it is equal to plus minus rl cos omega ct. So here we can use y minus y naught is equal to plus minus rl cos omega ct, where omega c is the cyclotron frequency. That means you can say here angular frequency. Okay, so let us put the value. Okay, let me scroll up the page. Okay, minus q, sorry, v perpendicular cos omega ct b plus again plus minus here on putting this value rl cos omega ct del b by del y. So now multiply. So here it will be b, then minus into plus minus, that's going to be minus plus. Okay, q v perpendicular cos omega cos square omega c t del b by del y. Okay, now let us find the average of the force along y-axis. Then how to find the average? Okay, now you see how to find the average of a function of t. Suppose we have a function of t, f of t, this is a function of t, then how to find the average of this? 1 by t, that means 1 by capital T, which represents time period 0 to t integration of f of t dt. Okay, f of t dt, that's how we can find. So how to find the average of cos omega ct? So here you see average of cos omega ct, that will be 1 by t capital T, this is time period, then integration 0 to t cos omega ct dt. So here on integrating cos omega ct, we will get sine omega ct by omega c. Okay, from 0 to capital T. Okay, so here you see so we can write this one as omega c into capital T, then here we can write sine omega c capital T minus sine 0. Okay, we can use right like this. So now you see what is omega c. So let me show you here this one, omega c. Omega c, it is nothing but 2 pi nu. Okay, nu means frequency, yes, which is equal to 1 by frequency is 1 by t capital T time period, so that's why it's gonna be 2 pi by t. Okay, so from here we get, from this we get omega c capital T, that's gonna be twice pi. So let us use this value here. Okay, let us use here. So here we can write 2 pi, then here it will be sine twice pi, sine twice pi, sine 0 is nothing but 0. Okay, now here you see value of sine twice pi is nothing but 0. Okay, value of sine twice pi is 0, so that's why, so this parts become 0. So average of cos omega ct is 0, so then we get minus plus, so average of cos square omega ct, let's find cos square omega ct. So I have done a mistake here, this rl is missing. Okay, this Lerma radius is missing here. So now let's find the average of cos square omega ct. Okay, so average of cos square omega ct, that's going to be given by 1 by t 0 to t cos square omega ct dt. Okay, so here you see, as we know that cos cos square theta is equal to cos twice theta plus 1 divided by 2. Let us use this identity here. Then 1 by t integration 0 to t, we will get cos twice omega ct by plus 1 by 2 dt. So half is taken common, then taken out, then it will be 1 by 2t, 0 to t cos omega 2 omega ct dt plus integration 0 to t 1 into dt is dt. Okay, this one. So now let us integrate. We will get here sine 2 omega ct by twice omega c from 0 to capital T, and plus here integration of dt is t from 0 to capital T here. So using the upper limits and lower limits, and you can multiply this now with both the term. So if you multiply, then what you will get here, 4 omega ct, then it will be sine twice omega c capital T minus sine 0, okay, then plus 1 by 2t into here t minus 0, okay. So then you see we can use this omega c capital T is twice pi, okay. So let us use this. So then it becomes 8 pi, and here it will be sine, here it will be 4 pi, sine 0 is 0, okay, then plus here 1 by 2t into t, here you see this t gone. So here you see one more thing, sine 4 pi is 0, 0 into anything is 0, so as a whole it is 0, and plus here we got half, okay. That means we have got average value of cos square omega c t is half, okay. So let us use this value here. So if you use this value here, then what you will get, half q v perpendicular rl del b by del y, okay. Now let me clean the part below where I have shown how to find average, okay. So let me delete this part, okay. So this is the average force along y-axis. So this is the expression for average force along y-axis. So this can be written as fy average, so half here minus plus q v perpendicular rl del b by del y, okay. This is the expression. So now let us find the expression for drift velocity of the guiding center along y-axis, okay. So you see drift velocity, okay. That is vc vgc, that's going to be equal to, here you see force F into B, that is by q b square. This is the expression, isn't it? We know this. So now here you see as we are now you see here we are going to use the y component of force only, average force along y-axis. So here it will be f of y cap cross, and magnetic field is being applied along z-axis, so b z cap, okay, then q b square by q b square, okay. So cross product of y cap z cap, that's going to be x cap. So that's why VGC will be Fy, average of Fy here into Bz. Instead of Bz, you can write directly B here, then QB square. So here X cap. Okay. So why I have written B? Here you see Bz means the Z component. Okay, and the magnetic field B is applied along Z direction. That's why Z component is simply B. You can write. Okay, hope you have understood this. So I have written like this. So now, yes, here you can see. So let us put the value of average Fy. So if you do so, then here you will get VGC, drift velocity of the guiding center. That's going to be equal to minus plus. So what is the value here? Half Q V perpendicular RL. So del B by del Y. Del B by del Y. So here we have got B X kept. Okay, then Q B square. Okay, so here Q will be cancelled, then this square is cancelled by this B, then you will get the expression of VGC, that is minus plus here twice B. We will get twice B as denominator, then B perpendicular RL del B del Y. Here we will get X cap, isn't it? Okay, so here you see this is I have written del B by del Y because the gradient, the grade B, is along y-axis. The variation of electric field lines is along y direction, isn't it? So that's why in the general form, this expression in the general form, okay, so we have got this expression. So in the general form we can write, okay, in the general expression, sorry, for drift velocity of the guiding center, just write drift velocity. Yes, okay, let me write the guiding center. Guiding center is given by VGC minus plus, so V perpendicular RL by twice B square grade B cross B. So we can write like this. Okay, so this is the general form. Okay, so here you see that means you may think here this is B only, here it is B square. So in this case we haven't cancelled the B square by B. Okay, so that's why we have got this expression. So this is how we can find the general expression for drift velocity, okay, while the grade B is along x, the motion of single particle in plasma under non-uniform magnetic field. Okay, so then the grip velocity is given by this expression. So I hope this video is helpful for you. If it is, then please do subscribe my channel and share my videos and like my videos. So thank you for watching.